So last class we had discussed the electric field charge distribution and I have assignment on distribution of line, surface and volume. So anyway, so we discuss. So first one is electric field due to line charge, and before that last class continuous charge distribution electric field discrete charge and summation integral E is equal to 1 by 4 pi epsilon 0 integral over 1 by r square r cap dq. R cap just a direction കാണിക്കാനാണ്. ഇനി first case നമുക്ക് line എടുക്കാം. Line case നമ്മുടെ equation എന്ന് പറയുന്നത് 1 by 4 pi epsilon 0 integral lambda by r squared r cap dl. അതായത് മേലത്തെ equationലെ dq എന്തായിട്ട് മാറി? Lambda into dl. dq is replaced by എന്താണ്? Lambda into dl. അവിടെ lambda എന്താണ്? Linear charge density. അത് നമ്മളൊരു ലൈൻ എടുക്കുവാണ്. അതിലെ ചാർജ് Q ഉം ആ ലൈനിന്റെ ലെങ്ത് L ആണെങ്കിൽ ചാർജ് per യൂണിറ്റ് ലെങ്ത് Q by L എന്തായിട്ട് എടുത്തു നമ്മള്? Lambda linear charge density. So lambda is equal to Q by L. Q ന്റെ SI unit എന്ത് വരും? Coulomb. Length ന്റെ SI unit meter. So linear charge density യുടെ SI unit എന്തായി മാറി? Coulomb per meter. So the equation of electric field for a line is 1 by 4 pi epsilon 0 integral over lambda by r square r cap into dl, where lambda dl is equal to dq. Now coming to surface charge density. So we have taken a surface with area A. Let Q be the charge on the area A. Then the surface charge density sigma is equal to Q by A with the SI unit coulomb per meter square. The electric field equation becomes 1 by 4 pi epsilon 0 integral over sigma by r squared r cap dA. Here dq is replaced by sigma dA. And coming to volume charge distribution, E is equal to 1 by 4 pi epsilon 0 integral over rho by r squared r cap d-tau. And rho into d-tau becomes dq. Here d-tau specifies the volume and rho is the volume charge density and rho is equal to q by v. So the first application of Gauss's law, that is the electric intensity at a point near a line charge. So going into the diagram, we have got a line of length L. Let the charge be Q, then Q by L becomes lambda. At a distance R, we have got a point P and we have to find the electric field intensity at the point P. And the electric field intensity is capital E. Now considering a Gaussian surface, that is a closed surface, and the total electric flux, that is surface integral E dot ds, that is a total electric flux through a Gaussian surface. Surface integral E dot ds is equal to E into 2 pi RL, that is area or the surface area of the cylinder, which is 2 pi RL. So the flux is E into 2 pi RL. Now applying Gauss's law, that is the total flux through a Gaussian surface will be equal to 1 by epsilon 0 times the net charge enclosed by the Gaussian surface. So here the flux is E into 2 pi RL. So this should be equal to 1 by epsilon 0 into net charge enclosed by the Gaussian surface. So here we have taken the net charge as lambda into L, where lambda is the linear charge density and L is the length. So Q by L is equal to lambda, or Q is equal to lambda L. Therefore, E is equal to 1 by 2 pi epsilon 0 into lambda by R. And next we have given a just vector notation where the vector E is equal to 1 by 2 pi epsilon 0 into lambda by R into R cap, where R cap is the direction. Next application, electric intensity due to a charged infinitely long straight cylindrical rod. So it has got cylindrical symmetry. So diagram okay. We have got a cylindrical wire or cylindrical rod. Okay, cylindrical rod of radius capital R. Let the volume charge density be rho and P is a point outside the cylinder at a distance r. We have to find the electric field intensity at the point P. Okay, so we are considering a Gaussian surface of radius small r. Okay, so we have to consider the Gaussian surface around the distribution with radius small r. Okay. ഇനി നമുക്ക് ടോപ്പ് ആൻഡ് ബോട്ടം റീജിയൻസ് ഉണ്ട് അല്ലേ? ആ ടോപ്പ് റീജിയൻ എടുത്താലും ബോട്ടം റീജിയൻ എടുത്താലും എന്തായിരിക്കും? അവിടെ നമ്മുടെ ഇയും ഏരിയയും എങ്ങനെയായിരിക്കും? പെർപെൻഡിക്കുലർ ആണ് അല്ലെ? ടോപ്പ് സർഫേസും ബോട്ടം സർഫേസും എടുത്താൽ ആ പ്ലെയിന്റെ ഏരിയയും നമ്മുടെ ഇലക്ട്രിക് ഫീൽഡും നോർമൽ ആണ്. അപ്പൊ ഫ്ലെക്സ് എന്താണ്? ഇ ഇൻറ്റു ഏരിയ. That is E dot ds, that is E ds cos theta. Here theta is 90 degree. So the flux is 0. എവിടെയൊക്കെ? നമ്മുടെ ടോപ്പ് സർഫേസിലും ബോട്ടം സർഫേസിലും. ഇനി നമുക്ക് നോക്കാം ബാക്കിയുള്ള കർവ് റീജിയനിലെ ഫ്ലക്സ് ആണ് നമ്മൾ പറയാൻ പോകുന്നത്. കർവ് റീജിയനിലെ ഫ്ലക്സ് നോക്കിയേ. The total electric flux through the curved surface is closed integral E dot ds is equal to E into area എന്താണ്? നമ്മുടെ സർഫേസ് ഏരിയ is 2 pi RL. സിലിണ്ടർ 2 pi RL. ലെങ്ത് നമ്മൾ L ആയിട്ട് എടുത്തു, റേഡിയസ് R ആയിട്ട് എടുത്തു. Therefore, total flux is E into 2 pi RL. Now applying Gauss's law, എന്ത് കിട്ടും നമുക്ക്? Flux is equal to, that is E into 2 pi RL is equal to 1 by epsilon 0 into net charge enclosed by the Gaussian surface. So here the net charge enclosed is rho into pi r squared L. That is rho is the volume charge density. That is rho is equal to, what is rho? Q by V. That is charge per unit volume. Here the volume of cylinder is pi r squared L. Therefore rho is equal to Q by pi r square, or Q is equal to rho into pi r squared L. That is net charge is rho into pi r squared L. Then E is equal to rho by 2 epsilon 0 into capital R square by small r. In vector form, vector E is equal to rho by 2 epsilon 0 into R square by R into R cap, where R cap is the unit vector or the normal. So here P is lying outside the cylinder. Now if P is lying on the surface of cylinder, that is small r is equal to capital R. Then the equation becomes E is equal to rho by 2 epsilon 0 into R squared by small r into R cap. Here capital R is equal to small r. Therefore, equation is rho by 2 epsilon 0 into capital R into R cap. That is one capital R and one small r get cancelled. Now the point P is lying inside the conducting cylinder. Okay. So inside the conducting cylinder, what happens? There is no charge inside, or the net charge is 0. So if the net charge is 0, E will be equal to 0. So that is, if a point P is lying inside the conducting cylinder, electric field is equal to 0 because the net charge inside the cylinder will be equal to 0. That is Q is equal to 0. Therefore, E is equal to 0. If the cylinder is non-conducting and the point P is lying inside the cylinder, what happens? So we told if the cylinder was conducting, the electric field inside the cylinder was 0 because the net charge inside the cylinder was 0. Now coming to non-conducting cylinder, what happens? The net charge is not 0. That is, the cylinder will enclose some charge which is equal to pi r squared L into rho. Rho is the volume charge density and pi r squared L is the volume. That is, Q is equal to V into rho. Or total flux is equal to E into area. E into area here becomes, for a cylinder, E into 2 pi RL. Now applying Gauss's law, E into 2 pi RL is equal to 1 by epsilon 0 times the net charge enclosed. That is 1 by epsilon 0 into pi r squared L into rho. Or E is equal to rho by 2 epsilon 0 into R. Or E is directly proportional to R for a non-conducting cylinder. So next application, electric intensity due to charged non-conducting sphere. The diagram has been shown. That's a sphere of radius capital R. Okay. And we have to find the electric field intensity at a point P outside the sphere which is placed at a distance of small r. And with that small r, we have drawn the Gaussian surface. Now let's go into the total electric flux through the Gaussian surface. How can we find? Closed integral E dot ds, that is E into area of the sphere. So it is E into 4 pi r square. To apply Gauss's law, we have to get the net charge enclosed by the sphere. So the net charge enclosed by the sphere will be equal to 4 by 3 pi r cube into rho. That is volume into rho, or volume into volume charge density. That is Q is equal to 4 by 3 pi r cube into rho. And applying Gauss's law, the flux E into 4 pi r square is equal to 1 by epsilon 0 into net charge enclosed by the surface. It is 1 by epsilon 0 into 4 by 3 pi r cube rho. From that, E is equal to, we get rho by 3 epsilon 0 into capital R cube by small r square, or it is equal to 1 by 4 pi epsilon 0 into small q by r square. In vector form also it is shown. So the second case, when the point P lies on the surface of sphere, what happens? The capital R and the small r become same, and the equation becomes 1 by 4 pi epsilon 0 q by capital R square, because capital R is equal to small r because the point P is lying on the surface. And the third case, when the point P lies inside the sphere. So what happens when the point P is lying inside? The total charge enclosed by the Gaussian surface is not zero. Why? We had already told, we are discussing about the non-conducting sphere. So for a non-conducting sphere, the net charge is not zero. And here, if the point B is lying inside, we can tell the small r is less than capital R, because small r is the distance between center of the sphere and the point P, whereas capital R is the radius of the sphere. So if the point B is lying inside, we can tell small r is less than capital R. And the charge enclosed by the Gaussian surface will be 4 by 3 pi r cube into rho. So the flux E into area, that is E into 4 pi r square, is equal to 1 by epsilon 0 into net charge, that is 1 by epsilon 0 into 4 by 3 pi r cube into rho, that is application of Gauss's law. And from that we can write E is equal to rho by 3 epsilon 0 into r, and converting rho, that is equal to q by 4 pi epsilon 0 into small r by r cube, and its vector form has also been shown.